All right, let's solve this equation. Let's solve cosine 2t equals cosine t. And we're just going to find the solutions between 0 and 2 pi. All right, so what are we actually doing? Well, let's take a look here. So let's graph the left-hand side on one line. So that's cosine, and we're going to use 2x. And the other side is x. And let's give ourselves some pi's on our x-axis here. Okay, now all we care about is the places where these two graphs intersect between 0 and 2 pi. So what we're actually trying to do is find the coordinates of these points of intersection. Okay, so let's start by getting that 2t out of there. So we know that the cosine of 2t, we've got a few options. We know we're going to have to solve this equation, so we're going to use the form of the double angle formula that only has cosines in it. So if we go take a look at that, we've got one right here. We've got cosine 2 alpha equals 2 cosine squared alpha minus 1. So cosine 2t equals 2 cosine t minus, 2 cosine squared t minus 1. So that means my equation can be written as 2 cosine squared t minus 1 equals cosine t. Pull everything over to the left-hand side, and we get 2 cosine squared t minus cosine t minus 1 equals 0. And we remember how to do this. We remember that we're going to factor this guy, and this factors as 2 cosine t plus 1 times cosine t minus 1. And those will equal 0. That means that 2 cosine t plus 1 equals 0, or cosine t minus 1 equals 0, which means that cosine t equals negative 1/2, or cosine t equals 1. We know from our knowledge of the unit circle that this means that t equals 2 pi over 3, or 4 pi over 3, and we know that cosine equals 1 when t equals 0. So actually, we stopped just before 2 pi, so there we go. So our solutions are 0, 2 pi over 3, and 4 pi over 3. The only thing we did different there was we used the double angle formula in the very first step. Okay, so let's do a word problem real quick here. All right, I got a cannonball fired with a velocity of 100 meters per second, launched at an angle of theta. Now here's what you might or might not know. Velocity is a vector, and it's really a vector with two different components. So when you think about a velocity that is going off at an angle, There's some part of that velocity that goes up. We generally call that v sub y. And there's some part of that velocity that goes horizontally. And we're going to talk about this later in the term a little bit more when we talk about vector addition. For now, just take my word for it. And if my angle of launch is theta, and that's an angle with the horizontal, unless stated otherwise, then the vertical component, the lift component of that velocity, is 100, is whatever your initial velocity is. So if this is, it would be, if this is v naught, it's v naught sine theta. And your horizontal velocity is v naught cosine theta. And if you take physics, you'll learn how to get this formula, but I'm just going to tell you that your height as a function of time is negative 4.9 t squared plus whatever your initial velocity is, multiplied by the sine of your launch angle, multiplied by time. So I always put that time out in front. You don't have to. The textbook doesn't. Just know that the time is not included in the sine. That is the vertical position of your launched object. The horizontal position, in other words, how far it goes away from launch, is given by your initial velocity multiplied by cosine of that angle multiplied by time. Okay, so there's our equations. Now, we've got a cannon that fires our projectiles with an initial velocity of 100 meters per second. And we want to hit a target 900 meters away. The question is, at what angle should we aim our cannon? All right, well, this isn't as hard as you think it is. So let's think about what we've got going on here. I've got my cannon right down here at the origin, and I'm trying to hit this target. And when I launch my cannonball, it's going to go up and come back down like this, right? So this is my height function. What I just graphed was my height. Now, it's also going to travel a certain horizontal distance. So here's how we're going to do this. We're going to first solve for the horizontal distance, and that will give us our time. That'll give us our flight time. And then we can use that time. Will that give us our flight time? Actually, we have to use both of these, don't we? We do. So think about this. I don't know time yet. So what have I got here? I've got an equation that gives me x as a function of time. I don't know time. I know that I think I want it to go for 900 meters, but that just would give me a theta and a time. I've got two unknowns. Oh, but that's okay, because I've got those same two unknowns in my height equation. So let's see. Let's see what we know here. What is my height when my cannonball hits my target? Well, it's 0, right? So I've got one equation. This is a 0 equals negative 4.9 times t squared plus 100 sine theta times time. And I've got another equation that says that 900 equals 100 cosine theta times time. The thetas in these two equations are equal, and the times in these two equations are equal, because when we are at time t, so this is time equals t. At that point, we know that h equals 0 and x equals 900. Okay, we can do this. So let's take these two equations and do some work with them. All right, we've got a couple of options here. What I'm actually going to do is, no matter what I do, things are going to get a little bit ugly, but let's do this. We're going to do some algebra. So let's take the second equation and let's solve that for time. Yes, that'll work. So time is going to equal 9 divided by cosine theta. Hopefully you can get to that point. I just divided both sides by 100 cosine theta. 900 divided by 100 is 1. Is that what I want to do? What's that going to give me in that second equation, on that other equation? Ooh, that's going to give me ugliness. So let's try this differently. Let's take this guy and solve it for time. If I do that, factor out the t. We get this, and that equals 0. So we're going to ignore the t equals 0 part because we start at height of 0, so we don't care. We know that one. But what we do know, what we want is that this also tells me that time equals 100 sine theta divided by 4.9. Oh, that's better. So now let's ignore this guy. It's still true, but it's not helpful. So what I'm going to do is I'm going to plug that in for time in this equation right here. So now I've got 900 equals 100 cosine theta multiplied by 100 sine theta divided by 4.9, which means that 900 equals 100 squared divided by 4.9 times cosine theta times sine theta. Well, that'd be really handy if I could had not cosine times sine. But I remember my double angle formulas tell me that cosine times sine is related to sine 2 theta. So, because I know that sine 2 theta would equal 2 sine theta cosine theta, that means that I know that sine theta cosine theta is equal to 1/2 sine 2 theta. Oh, that's handy. So now what I have is 900 equals 100 squared divided by 4.9 times 1/2 sine 2 theta. All right, if I crunch a few numbers and do a little work, so here's what I know. I'm going to end up with sine 2 theta equals 900 times, I can do 4.9 times 2 is 9.8. I'm going to divide that by 100 squared. So 2 theta is equal to the inverse sine of all of that. And if I do that on Desmos, keep yourself in, we want in degrees, so let's put ourselves in degrees over here. Degrees. And what I want is the inverse sine of 900 times 9.8 divided by 100 squared. And I get 61.88. Now, that does not mean I'm going to launch my cannon at 61 degrees, because that's 2 theta. So I'm going to divide through by 2 in order to get theta equals 30.94 degrees. And that is the angle at which I should set my cannon. All right, we're going to talk just briefly in the next video about the power reduction and half angle formulas. They're pretty straightforward. They are an outcome of the double angle formulas. And then we'll do a couple of examples.